It's time now to talk about the derivatives of trig functions. Now, we've talked about the derivatives of polynomials, rational functions, and basically the variable to any real power, such as square roots and cube roots. However, we need to expand our repertoire of functions that we can find the derivative for. In this section, we're going to look at the derivative of the major 6 trig functions. We'll take a look at the derivative of the inverse trig functions in a later section. Now, when we look at these types of functions, they describe oscillatory behavior, such as a weight on the spring bouncing up and down. But sound waves and, well, what else? Vibrations also use trig functions to describe and model their behavior. So it's important to add this class of functions to our repertoire. Now, there are some patterns that we're going to see here. For example, when we consider tangent and secant, they have cofunctions. The cofunction of tangent is cotangent, and the cofunction of secant is cosecant. Any derivative that starts with co is going to have a negative attached to the derivative. So the derivative of cosine is negative, derivative of cotangent is negative, and the derivative of cosecant must be negative. The other three, in fact, the primary three, sine, tangent, and secant, are all positive. When we look at tangent, its derivative is secant squared. There is a pattern. The derivative of cotangent is negative cosecant squared. In other words, the same function, but with co attached at the front and a negative. The pattern holds for secant. The derivative for secant is secant tangent, and the derivative of its cofunction, cosecant, is going to be negative cosecant cotangent. There are some patterns like this to help you memorize these, but in fact, you're just going to have to memorize them. These are not things I'll allow you to write down on a formula sheet. You need to know these and know them well because they come up frequently in calculus. Let me share my screen and we'll get started. Our learning objectives are relatively simple. Find the derivative of sine and cosine. Find the derivative of the other 4 standard trig functions, tangent, secant, cotangent, and cosecant. And then calculate the higher order derivatives of sine and cosine, where we'll discover a pattern we will exploit to the max when we get into calculus 2 and series. We're going to start with our building block trig functions, sine and cosine. Let's go ahead now and take a look at the derivative of sine. The derivative of the sine function is, in fact, cosine. We're going to need a couple of limits that we learned earlier in order to prove this. The first is the limit as h approaches 0 of sine of h over h, whose graph you see here on the left. It is obviously not defined when h is 0, but it approaches from both the left and the right the y value of 1. So the limit is 1. We also need the limit of the cosine of h minus 1, all divided by h. Again, it obviously cannot exist at 0 since that would cause division by 0, which is never allowed in our numeric system. Then, when we look at the limit of this and we observe the graph from the left and the right as x gets closer to 0 from both sides, we see that it approaches and is aimed directly at that y value of 0. So this limit is 0. Now, when you think about the sine graph, again, you could have drawn the derivative from the graph of sine, and you would have noticed probably that it looked a lot like cosine. But let's prove that now. Here's the proof that the derivative of sine is cosine. We start, as always, with the definition of the derivative, which is the limit of the difference quotient. We're choosing to use the x plus h form of the difference quotient. Then we take and we apply a trig identity for the sine of a sum. The sine of a plus b is sine of a cosine b plus cosine a sine b. We use that to split up the sine of x plus h into sine of x cosine h plus cosine x sine h. We still have the minus sine x in the numerator. And of course, it's all divided by h, and we're taking the limit of it. The next thing we do is we split it into two different fractions with the same denominator, h. We take the terms sine x cosine h minus sine x and divide that by h. Then we isolate the cosine x sine of h divided by h in a separate fraction. The reason is we want to factor out the common sine x from these two terms. When we do that, notice we get that limit that we know approaches 0. For the second term, we factor off the cosine of x, which results in sine h over h, which is the other limit that we said we would need. Now what we do is we apply the rules for the limit laws. The limit of a sum is the sum of the limits. Limit of a product is the product of the limits. This lets us split it into 4 different limits. The limit as h goes to 0 of sine x is just sine x because there's no h to substitute. However, it is multiplied by the limit cosine h minus 1 divided by h, which approaches 0. Sine x times 0 is going to be 0. The second term gives us the limit of cosine of x as h approaches 0. There's no h, so it's just cosine x. It's multiplied by the limit of sine h over h, which we know approaches 1 as h goes to 0. That gives us cosine x times 1. And of course, this results in cosine of x. And we end our proof with quod erat demonstrandum, which means that which has been demonstrated. Now let's go ahead and look here at the relationship between the sine graph and its derivative. When we look at the relationship between the two, I'm going to go ahead and highlight the sine graph in yellow so it pops out a little bit more. Let me make my yellow a little bit smaller. And here is the graph of sine, which we know begins at the origin and has a bubble up, crosses through the x-axis at pi, and then a bubble down coming back up. Notice that it is concave down between 0 and pi, and concave up between pi and 2 pi. Also notice that it has a maximum, relative maximum of 1 here at the value of pi over 2. Because that's a maximum, in the graph of the derivative, we'll have an x-intercept directly below it at pi over 2. It also has a minimum value of 1 at 3 pi over 2. Not 1, but negative 1 at 3 pi over 2. Which again corresponds to an x-intercept on the graph of the derivative. Then we can examine the slope of the tangent line to predict what the derivative is doing. At the origin, it is positively sloped, and in fact, the slope is 1. Then it decreases in value until it reaches pi over 2, which you see here. Then it becomes a little negative, then more negative, more negative, more negative, and there's an inflection point directly at pi. That inflection point right there becomes a minimum on the graph of the derivative. Then when we come down, it stays negative, but it is approaching 0 again, so the derivative does that behavior. Then it starts to go up again. Notice that we'll also have an inflection point at 2 pi, which corresponds to a maximum in the graph of the derivative. Now, if you found that the derivative of sine is cosine, and you know that the graph of sine and cosine are really just phase shifted over from one another, then it sort of makes sense that the derivative of cosine would have something to do with sine. And in fact, it does. The derivative of cosine, it's a co-function, so it must be negative, and the derivative is negative sine of x. The proof of this is very similar to the proof for sine. Let's work some examples now, finding and using the derivatives of sine and cosine. These you must memorize. The derivative of sine is cosine. The derivative of cosine is negative sine. In the first example, you'll want to use the product rule. This is sine of x times cosine of x. In example 2, you'll need the product rule. This is x divided by the cosine of x. Pause the video now to work out the solutions. So how did you do? Let's take a look at what we have. We have the product of two trig functions, so we'll use the pattern f prime g plus g prime f. The first factor is sine of x. The derivative is cosine. So the derivative of sine x becomes cosine. We multiply by the second factor unchanged. Cosine of x times cosine x gives me cosine squared x. You can either write the cosine x in parentheses with the square outside, or you can place the 2 between the cosine and the x. Then for the second term, we take the derivative of the second factor, which was cosine. The derivative of cosine is negative sine of x. And then we multiply by the first factor unchanged. This gives us minus sine squared of x, or sine of x quantity squared. Cosine squared of x minus sine squared of x becomes cosine of 2x. This particular trig identity comes up often enough that you should probably recognize it. There is another double angle formula that comes up a whole lot, and you will definitely need to recognize that one. When we get to it, I'll let you know what it is. Now we want to look at example 2. In example 2, we have the ratio of a polynomial x with a trig function cosine of x. We apply the quotient rule for derivatives, f prime g minus g prime f over g squared. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Whatever pattern you memorized, use the same pattern every time you do the quotient rule to help create a rut in your brain so that memory stays there forever. This means that we need to take the derivative of the numerator, which is x. Derivative of x is going to give us a 1. Then we multiply by the denominator, cosine x unchanged. That will give us 1 times cosine x, or cosine x. Then we subtract the derivative of the denominator, which is cosine x. That gives us a negative sine x. That negative is not the subtraction in the formula. It's going to give us a double negative. Then we multiply by the numerator factor unchanged. Do not leave that x factor at the back of sine x. It's going to start to look like sine of x squared, and it is not. It is x times the sine of x with the double negative giving us a positive. Finally, we divide by cosine squared of x. And again, it can also be written in this form here with cosine x in parentheses and the square outside. Let's now take a look at example 3, and we'll work this one together. We have a particle moving along a coordinate axis. Its position at time t is given by the function s of t equals square root of 3 times t. The t is not under the radical, plus 2 times cosine t. And our time period is restricted to 0 to 2 pi to restrict our solutions. We want to know when the particle is at rest. In other words, it's not moving, which means the velocity is 0. Velocity is the derivative of position, so let's find the velocity function now. The velocity function is the first derivative of position. In this case, the square root of 3 is just a constant, and the square root of that 3 times t, the derivative will just be square root of 3. Then we have plus 2 cosine t. You know the 2 is a constant that can be pulled out, so it will still be there. And the derivative of cosine is negative sine. So we get negative 2 sine of t. Now let's go ahead and find when the velocity is equal to 0 on the interval from 0 to 2 pi. When we're looking at that, we're going to set the velocity equal to 0 and find t. This means the square root of 3 minus 2 sine t equals 0, or the square root of 3 equals 2 sine t. Isolate as much as you can the t. Divide both sides by 2 to get root 3 divided by 2 equal sine t. Now, what angle between 0 and 2 pi causes a value of square root of 3 over 2? It's positive, so it must be in either quadrant 1 or 2, where sine is positive. I say sine, you think y. I say cosine, you think x. It's going to be positive in those two quadrants. What angle gives a square root of 3 over 2? When we think about the angles, we either have a 45, 45, 90 triangle, where the sine and cosine are identical, square root of 2 over 2, or 1 over the square root of 2, or we have a 30, 60, 90 triangle, where one value is 1/2 and one value is square root of 3 over 2. This is obviously the 30, 60, 90. Square root of 3 over 2 is larger than 1/2. This must be, if we think about our unit circle, the tall but skinny triangle. And yes, those are supposed to be the same side. This must be the square root of 3 over 2. This is 1/2. This would be, well, negative 1/2, but 1/2 in length. And this is square root of 3 over 2 again. Those angles are going to be pi over 3 and 2 pi over 3. Make sure that you give the solutions in terms of radians. When we're computing the derivatives of sine and cosine, the formulas only work if the angle is in radians. The formula, if the angle is in degrees, is not the same as if the angle's in radians. So your angles must be in radians. In calculus, we almost always work in radians. In physics, sometimes we work in degrees, which means there's a lot of converting from one system to the other. Let's now take a look at the next two problems. Examples 4 and 5 combine some more different rules that we have for derivatives. In problem 4, you have y equal x minus x cubed sine of x, and we want to find the derivative of y, or y prime. Notice that we've got a difference, so we can apply the difference rule for derivatives, and a product, so we can apply the product rule for derivatives, and the power within the product, so we'll need the power rule. Coming down here, you have a couple of options. You could multiply it out, but I will warn you that you're not going to avoid the product rule. You might as well use it from the beginning. Even when you multiply it out, you're going to get a cosine and sine multiplied together. The product rule will have to be used. Go ahead and pause the video, work them out, and then we'll turn it back on to check our answers. Let's look at the results together. In the first problem, example 4, we take the derivative of the difference as the difference of the derivatives. That does work for derivatives and limits. In fact, it will also work for integrals. However, product and quotient rules for derivatives are totally different than what we have for limits. And in integration, well, there really isn't a rule. There are a lot of techniques to try to work those out. We take the derivative of each term individually. The derivative of x is 1. Then we apply the product rule to the second term. X cubed becomes our f, sine of x is our g. The derivative of x cubed is 3x squared. Then we multiply by g, which is sine x. Add to that the derivative of g, which is going to be cosine, times f unchanged. When we work it all out, we get the result 1 minus 3x squared sine of x minus x cubed cosine x. Example 5 is more complicated. There's more simplification to do and more rules to apply. I probably should have allowed more space. You could multiply it out first and then take the derivative, or you can take the derivative in the beginning. I chose to apply the product rule at the beginning, but I'm now wondering if maybe it would have been easier to multiply it out and then do the product rule. In this case, I'm going to take the derivative of the first factor, x plus cosine of x. This is a sum, and the derivative of a sum is the sum of the derivatives. Derivative of x is 1. Derivative of cosine x is negative sine of x. Then I multiply by the second factor unchanged. This is the identical binomial type form. So when I multiply it out, note that I get 3 terms, not 2. The outside and inside product double. Then I'm going to take the derivative of the second factor and multiply by the first factor. The derivative of the second factor has a 1 minus sine x, so I get 0 minus cosine x. The derivative of sine is positive cosine, but the negative is already there. So it becomes negative cosine. I multiply these out, and then I look at the format that I have. I notice that I have a sine squared and a cosine squared with opposite signs. That's the double angle for cosine. So I factor out the negative and I rewrite it in the simplified form here. I don't know if we have enough space, but let's give it a shot and see if we come up with the same thing if we multiply it together first and then take the derivative. In that case, let me come over here, and I may have to use some space up there. We'll see. If I multiply y out first, this is going to give me for the first times the first x, on the outside minus x sine x, on the inside plus cosine x, and for the last minus sine x cosine x. I think I've changed my mind. I don't think this would be simpler. Why? Take a moment, look at the structure, and think about the derivative rules you would have to apply to find this out. I would stop here and go back to the original that I did, because I recognize I now have 2 factors, x sine x and sine x cosine x, that will require the product rule. In this case, it was better to do it from the beginning. Let's now take a look at example 6, and we'll work this one together. In example 6, we want to find the equation of the tangent line to both of these functions that we see here, and then we want to use some kind of graphing utility, I recommend Desmos, to graph both the function and the tangent line to ensure we've got the equation of the tangent line correct. This is really 2 different problems put into the same example. For this one, we're going to focus first on the function negative sine x at x equals 0. We know we want the equation of the tangent line, so we need the point on the actual function. That means f of 0. So the first thing I'm going to look for is f of 0, which becomes negative sine of 0, but the sine of 0 is 0, and negative 0 is 0. This gives me the ordered pair 0, 0. Now I need the slope of the tangent line. Have the point x1, y1. I need the slope of the tangent line. To do that, I take the derivative of the function. The derivative of my function, I think I have more space. Yes, I do. All right, is going to give me negative cosine of x. I need to know what it is specifically when x is 0. So then I substitute 0 in place of the variable. And it would help if I wrote that. And this gives me negative cosine of 0. The cosine of 0 is 1, so this gives me negative 1. Then I can write the equation of the line, y minus the y coordinate of 0 equals the slope negative 1 times x minus the x coordinate of 0, which simply reduces to y equal negative x. Let's take a look at the graph now and make sure that this fits. Does it look like we have the tangent line? It's very close to the curve right here. You can tell that in this region, the tangent line is a good approximation to the curve. To be sure, you can scroll in closer and closer, and you can detect that, in fact, it is tangent at that one point. Let's now take a look at the second part to example 6. 1 plus cosine x is the function at the point x equal 3 pi over 2. When we look at this one, we again need the point on the function itself. So we substitute 3 pi over 2 into the function. This is going to give us 1 plus the cosine of 3 pi over 2. But cosine is 0 at all pi multiples of pi over 2. And that means that this is 0. So we get the x coordinate, or rather the y value of 1. And this gives us the ordered pair 3 pi over 2, comma 1. Now we need the slope at that point. So we take the derivative of the function, 1 plus cosine x. The derivative of that function is going to give me negative sine of x. Then I substitute 3 pi over 2 in place of the variable to find the slope specifically at that point. The sine of 3 pi over 2 is a negative 1, so I get a double negative, which gives me a slope of 1. And I write the equation of the tangent line, y minus 1 equal 1 times x minus 3 pi divided by 2. Let's check the graph and make sure that it fits. Coming over here at 3 pi over 2, I can scroll in and in and in, and I can detect that that is in fact the tangent line at that point. Let's turn our attention now to the other trig functions. We've kind of done sine and cosine to death. It's time to talk about tangent, secant, cotangent, and cosecant. You need to memorize these formulas. You need to do it as quickly as possible because they're going to be coming up over and over in different problems. You will see these on exams and quizzes. The derivative of tangent is secant squared. There's a pattern for the co-function cotangent. It starts with co, so it must be negative. Since the derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared. Then the derivative of secant is secant tangent. Memorize it as quickly as you can. The derivative of its cofunction, cosecant, must be negative cosecant cotangent, and it is. There is a pattern, and it will help you to memorize these 6 different trig derivatives. Let's use the quotient rule and the derivatives of sine and cosine to prove that the derivative of tangent is secant squared. Yes, as long as you know sine and cosine's derivatives, you could, in fact, go ahead and compute the derivatives of the other 4 using product rule and quotient rule. Let's do this now. So we want to find the derivative of tangent of x. To do that, we need to use the definition of tangent. Tangent is equal to sine divided by cosine. That means that the tangent of x is equal to sine of x divided by cosine of x. To find the derivative with respect to x of tangent of x, I'm going to apply the derivative to the quotient of sine and cosine. This is going to give me that formula that we use, which is going to be f prime g minus g prime f over g squared, where sine of x is f and cosine is g. Let's apply the formula now. I need the derivative of sine multiplied by cosine minus the derivative of cosine times sine. And I'm going to divide it all by the cosine squared. The derivative of sine is cosine. So this gives me cosine x, or cosine squared of x. Then for the second part, the derivative of cosine is negative sine, and then multiplied by sine. I have a double negative, which is going to make it positive. That gives me cosine squared of x divided by, or plus sine squared of x divided by cosine squared of x. Don't simplify, simply look at that cosine squared plus sine squared and remember your Pythagorean trig identity. That's the value of 1, which means that we end up with 1 over cosine squared, which reduces to secant squared of x. And that's what we were trying to prove. You need to memorize the derivative of tangent as secant squared. Let's now find the derivative of secant. First, we need to define what secant is. Secant of x is equal to the reciprocal of cosine of x. Now that we have the reciprocal, we can apply this by taking the quotient rule. The quotient rule in this case is going to have f as 1 and g as cosine x. Again, we're using the formula f prime g minus g prime f divided by g squared. The derivative of secant then becomes the derivative of that formula. We will learn something called the chain rule, which will greatly simplify finding these quotient derivatives. This now gives me the derivative with respect to x of 1 times cosine x minus the derivative with respect to x of cosine x times the 1, all divided by cosine squared of x. Now the derivative of 1 happens to be, yes, 0. And that is going to give us sorry, I had a brain meltdown there for a moment. I lost my train of thought completely. Okay, what does that give us? The derivative of 1 is 0, which eliminates the first term. And then the derivative of cosine is negative, so we get a double negative sine of x times 1 over cosine squared of x. This gives me sine x divided by cosine squared of x. The next part is sort of a little tricky. What we're going to do is we're going to manipulate the denominator, and we're simply going to rewrite this in a different form as the sine of x divided by 1 factor of cosine x times a 1 divided by the other factor of cosine x. The rules of multiplication of fractions tells me that these two are equivalent. The first factor, sine x divided by cosine x, turns out to be the definition of tangent of x. And the second factor, 1 over cosine x, is in fact secant of x. It is our habit, though, I will tell you, to write the derivative of secant as secant x tangent x. That's the order we typically stick to. Let's now turn our attention to examples 8, 9, and 10. In 8 and 9, you're to use the derivatives of cosecant, tangent, and cotangent, and the product rules, difference rules, and sum rules for derivatives. In example 10, instead, we're looking for the slope of the tangent line at a particular point. We worked several examples like these, so pause the video now to try these examples on your own. Here again are examples 8 and 9. Let's look at example 8. We have a function cosecant of x plus x times tangent of x. In the second term, we will need the product rule, where x is the first function and tangent of x is the second. When we take the derivative of cosecant, we get the negative co-function of the derivative of secant. The derivative of secant is secant tangent, so we get negative cosecant cotangent. Then we add the result of the product rule, 1 tangent of x plus x secant squared of x. There's probably not a great deal we can do to simplify this. I would just leave it in this form. Let's now look at example 9. We have the difference of two terms, 2 tangent of x minus 3 cotangent of x as our function. We won't need the product rule because the 2 and 3 are constants. It can be factored out of the derivative and then multiplied when the derivative is found. The derivative of tangent is secant squared, so we multiply it by the 2. The derivative of cotangent is a negative because it starts with co, and it will be the co-function of the derivative of tangent, which was secant squared, so it becomes negative cosecant squared. The double negative will give you a plus, and again, there's probably not much point in trying to simplify it. Just leave it in this form unless there's something specific you need to do with it. Let's now look at the tangent line problem in number 10. Our function is tangent of x, and we're interested specifically when x is pi over 6. To write the equation of the tangent line, we need the point on the function, So we substitute pi over 6 into tangent. Tangent you can think of as sine divided by cosine, since you probably don't have the tangent of pi over 6 memorized. Remember, pi over 6 is a low, long triangle in quadrant 1. It's got to be the 30, 60, 90. So the short side is a half, and the long side is square root of 3 over 2. When I say sine, you think y. When I say cosine, you think x. That means the sine of pi over 6 is 1/2, and the cosine is root 3 divided by 2. That gives us a complex fraction, which remember that the top of the top and the bottom of the bottom are on top, and the ones sandwiched in the middle go to the denominator. That would give you 2 over 2 root 3, and the 2's cancel to give you 1 over the square root of 3. Write this as a point in ordered pair form. Now we need the slope of the tangent line by finding the derivative of the function. The derivative of tangent is secant squared. Now we need the slope specifically when x equals pi over 6. So I evaluate secant squared at pi divided by 6. I don't have that memorized, but I know secant is 1 over cosine. I chose to write the cosine in parentheses with a square outside to make the notation easier to follow. I've already found the cosine of pi divided by 6 in my picture here. I know it is root 3 divided by 2, so I square it to get 3 divided by 4. It's important in a complex fraction to keep track of which one is the primary division bar. The primary one is the one between the 1 and the 3/4. That makes 4 the bottom of the bottom, so it flips to the top. And we get a slope of 4/3. Write the equation of the line as y minus 1 over root 3 equal 4/3 times the quantity x minus pi divided by 6. We have 2 more examples to work in this section, examples 11 and 12. In example 11, you will use the sum rule for derivatives. You can use the quotient rule on the 5 divided by x, but you can also instead rewrite this in a slightly different form that's easier to apply the derivative rules. I can rewrite 5 divided by x as 5 times x to the negative 1 power. And then I can apply the power rule for derivatives. For the second example, number 12, I will need to apply the quotient rule. There's no way around that at this point in time. After next section, though, you will have an alternative method for finding the quotient rule. Pause the video, work these out, and then we'll compare. Example 11 is relatively straightforward when you recognize that you can rewrite the quotient of 5 and x as 5x to the negative 1 power. The derivative of cosecant is a negative cosecant cotangent, which gives you negative 3 cosecant cotangent for the first term. When you apply the power rule, the negative 1 comes to the front and you reduce the power by 1 to negative 2. That gives us negative 5 in the numerator, and the x to the negative 2 can be rewritten as x squared in the denominator. However, I would take it if you wrote negative 5x to the negative 2. They're equivalent and both are correct. Looking at example 12, it is much more complicated. There is, in fact, some reduction that can be done at the end, which you probably did not recognize. You probably stopped too soon. How do you know when to keep going and when to stop? If you feel like you're getting somewhere and things are getting simpler, keep going.
If you feel like you're not getting anywhere, and you've fallen down the rabbit hole, or things are getting more complicated, stop and back up. In this case, we're applying the quotient rule. We have the derivative of tangent, which becomes secant squared, times 1 minus secant x. Then when we multiply it out, we get secant squared minus secant cubed. Minus the derivative of the denominator, which gives us a negative secant x tangent x. The derivative of secant is positive, but it has a -1 multiplied by it. That's why it's negative. And then it's multiplied by tangent of x, which gives us positive secant x tangent squared of x when we subtract it. Notice that every term in the numerator has a common factor of secant. So the next step, I factored out the common factor of secant, which left me with secant x minus secant squared plus tangent squared in parentheses. Tangent squared minus secant squared is a Pythagorean trig identity, which you are expected to know. It is the value of 1, which gives us secant x minus 1. Can you see that it's getting simpler? This is why I kept going. Now, I recognize that secant x minus 1 is the opposite of what I have in the denominator. So I factor the -1 out of that term, so they're identical. Then one of these cancels 1 in the denominator, and my final result is a far simpler negative secant x divided by 1 minus secant x. There's no reduction that can be done because it is the denominator that has multiple terms. You're going to have to leave it like this. We turn our attention now to higher order derivatives. This is the last part of this particular video. Throughout the calculus sequence, we work a lot with higher order derivatives. It becomes a big part of series when we look at Taylor series and Maclaurin series in Calculus 2. We worked with them as well in Calculus 3. They just come up very often. In particular, we want to exploit a pattern that both sine and cosine have. They have a repeating pattern every 4 derivatives. The pattern repeats. Let's take a look at the pattern for sine. When we write the 0th derivative, we mean don't take the derivative. I know that sounds kind of crazy, but you'll use this notation again when we get into Calculus 2. The 0th derivative means you've taken the derivative 0 times, so it's still the function. We're starting with sine of x, and we take the derivative once to get cosine. Then we take the derivative again to get negative sine. When we take the derivative of negative sine, we'll get a negative cosine. But the derivative of negative cosine will give me a double negative, and I'll come back to sine, which means I'm starting again with the beginning, which means after 4 derivatives, I'm back where I started and the pattern repeats. This means that it doesn't matter how many derivatives I've taken, I can figure out where in the pattern of 4 it is and know exactly what the derivative is. So for example, when I'm looking at d to the 9th, I know that it's got to be similar to d to the 5th because it's a pattern of 4 apart. This also has to be the same as the first derivative because that's a pattern of 4 apart. And that tells me that it's got to be cosine of x. Now, when I'm doing these on a example or a problem, let's say the 33rd derivative, what I actually do in practice is I take 33 and I divide it by 4. If I take 33 and I divide it by 4, I end up with 8 with a remainder of 1. It's the remainder I'm looking for because that tells me where in the pattern it is. It completed the pattern of 4 8 times, which just means it kept going back to the beginning, but then it did it one more time. That means that the 33rd derivative of sine must be cosine. And we would write it using this notation here. It's got to be the same as the first derivative. What if I were to use the 67th derivative? Divided by 4, I end up with 16. I think that's right. But the remainder is 3. Therefore, it is the third derivative of sine. And the third derivative of sine would be, let's see, I'll have to scroll up, negative cosine of x. Let's practice this now in examples 13 and 14. This is so short, there's not probably any reason to pause the video. To find the 59th derivative of sine, what I want to do is take this pattern and divide the 59 by 4, which just tells me that it's repeated that number of times. And I have a remainder of 3. So the 59th derivative of sine must be equivalent to the third derivative of sine, which we found to be negative cosine. I hope this is making sense to you and that you're not totally confused. Let's take a look now at the next one. This one involves cosine. First, we want to find the first 5 derivatives of cosine and see if it has a pattern like sine does. And if it has a pattern, how many derivatives it takes to repeat. Because sine and cosine are phase shifted, and they're really the same graph, just shifted over, we should expect that the pattern is an identical 4. Let's prove that now. The first derivative of cosine gives me negative sine. The second derivative of cosine is the derivative of the first derivative, which would be negative cosine. The third derivative of cosine would be the second derivative of the first derivative, or the first derivative of the second derivative. Basically, take the derivative again, which would give me a double negative, which would lead me to sine. And then when I take the fourth derivative of cosine, I end up with cosine again. In other words, I'm back to the beginning. It does repeat every 4. The derivative of cosine is negative sine. The derivative of negative cosine is positive sine. And the derivative of sine puts me right back to the beginning at cosine. So if I have the 579th derivative of cosine, I take the 579 and I divide by 4. I'm not really interested in the quotient. I'm really interested in the remainder. 4 goes into 5 one time with 1 left over. 4 goes into 17 4 times with 1 left over. 4 goes into 19 4 times with 3 left over. The 579th derivative of cosine has to be equivalent to the third derivative of cosine, which we found to be sine. Let's now look at an application problem in number 15. In this particular problem, we have some kind of block or weight attached to a spring, a coiled spring, attached to some ceiling or something. If I pull on the weight, it will oscillate up and down. And this can be described with a trig function. Its position at time t for rest is given by 2 sine of t. I want to find both the velocity and the acceleration at the point in time 5 pi divided by 6. Then I want to compare these values and decide whether the block is speeding up or slowing down. In order to find the velocity, I need to find the derivative. So I take the derivative of 2 sine t. The derivative of sine is cosine, so I get 2 cosine of t. Now I need to take the derivative of the first derivative to get the acceleration. The acceleration will be the derivative of 2 cosine of t, which becomes -2 sine of t. Now I want to think about what these values are at 5 pi over 6. Let's visualize where 5 pi over 6 is. It's in quadrant 2, but it's a low long triangle. The y value must be positive, but the x value must be negative. That means that the sine will be 1/2 and the cosine -√3 divided by 2. Let's now find the velocity at 5 pi divided by 6 by substituting that into 2 cosine of t. This gives you 2 times a -√3 over 2, which becomes a -√3. This would be probably a -√3 inches per second. Something that relates to velocity. Now let's take a look at the acceleration at the same point in time. The velocity is negative, which if I call up positive and down negative, means that it's moving down. I don't know whether it's above or below equilibrium, but the motion is down. When I find the acceleration at 5 pi over 6, I need to substitute that value into -2 sine of t. The sine of 5 pi divided by 6 is 1/2, which gives me a -2 times 1/2, which would give me a -1. And this would probably be inches per second squared. Since both the velocity and the acceleration are negative, what does that tell you about the particle? Is it speeding up or is it slowing down? Because they're both negative, the combination of signs is a positive, so in fact, it is speeding up. Let's take a look at the function in example 15 and see why, in fact, it's speeding up. Our function is 2 sine of t, and our point is 5 pi over 6, 1. Let's take a look at that graph now. When you look at the graph, here is what we see. When we're looking at this, the point that we're interested in is right here. You'll notice that on this section of the graph, the curvature is concave down, which means the second derivative is negative. As we found, the acceleration is negative. It is also just to the right side of a maximum, which means that it is speeding up because it has not yet reached the inflection point. The place where the graph connects here at pi, at the inflection point, is where it changes curvature from concave down to concave up. It's also where the particle stops speeding up and starts slowing down. Or on the next one, stops speeding up and starts slowing down. Well, I guess it's the same on both. When I'm looking at this one is speeding up after being stopped until it reaches the inflection point, and then it will start slowing down as it approaches the next location where the velocity is 0. We have two more examples to work in which we're going to find higher order derivatives. In 16, I want you to take the derivative of cosecant 2 times. In other words, take the derivative of cosecant, then take the derivative of the derivative. For 17, we want to find the second derivative of this equation here. Go ahead and pause the video, work them out, and then turn the video back on to check your answers. So let's see what we get for example 16. I took the first derivative of 2 cosecant x to get negative 2 cosecant x cotangent x. That's a product, so I will need the product rule. To take the derivative of the first part, I attach the negative 2 to the cosecant, so I have only 2 factors. The derivative of cosecant is negative cosecant cotangent, but I also had another negative, which gave me a double negative, resulting in a positive, 2 times cosecant cotangent. And then I multiply by the second factor, cotangent, unchanged. Then I add to that g prime times f, which is a negative cosecant squared times the first factor, negative 2 cosecant. When I simplify this, I got 2 cosecant x cotangent squared of x plus 2 cosecant cubed of x. Notice they had a common factor, so I factored it out to see if it made it simpler. Then I noticed I had cotangent squared plus cosecant squared. With tangent and secant, cotangent and cosecant, I have to have opposite signs to be the Pythagorean identity, which told me I needed to stop. It wasn't going to get simpler. You could either leave it in one of the 2 forms written here. Let's look at the last example, number 17. In 17, I've gone ahead and I've simplified it more by doing some of the work in my head instead of writing out the derivative notation each time. As we progress through the course, this is going to become my habit. If you get confused, always remember that you can write the derivative notation before you take the derivative. Our function is 3 sine x plus cosine squared times cosine x. The derivative of the first term is just 3 cosine of x. The second term has a product of 2 functions of x, so I need the product rule. I did the derivative of x squared in my head to get 2x, multiplied by the second factor cosine x. Then I added the derivative of cosine x, which is negative sine x, and multiplied by the first factor, x squared. In simplifying, I got the expression here highlighted in yellow. 3 cosine x plus 2x cosine of x minus x squared sine x. I didn't see any common factors and I didn't see any hiding Pythagorean identities, so I knew that I wanted to stop. In the next video, we're going to discuss the chain rule, one of the 3 most important sections in all of Calculus 1. When we look for a concept that we really want our students to know coming out of Calculus 1, chain rule always makes the top 3. It's vitally important that you learn that section really well, and it will give us an alternative to the quotient rule. I'll see you in the next video for the chain rule.